Good afternoon, students. Welcome to the final live session on finite element method, variational methods to computer programming. So, if you have any queries, doubts, you can put it in the chat box. I will try to address. So, I will address those issues. I will wait for some time. Otherwise, I will discuss the last assignment that is already being submitted by you. That is assignment 9. Maybe you can switch to PDF. So let us go through the assignment 9. The first problem, you have been given a mesh. As you can see, the mesh, the actual domain is a hexagonal domain, and it has been discretized using triangular elements. So, and these numbers, basically encircled numbers in blue, that denotes the element number. The numbers in blue denotes the local number, that is basically the node numbers of each of the elements, and then the black numbers basically denotes the global node numbers, right? So this is explained in the question. Now here we just intended to understand whether you have understood the assembly process. All right. Now here, since I have given only one number, I have assigned only one number to each of the nodes. So basically I am looking for a single variable problem. Okay. So you have only one dependent variable. Fine. So when we will denote say Kij, when there is no superscript here, so this will denote the global stiffness entry, okay, ijth entry of the global stiffness matrix. Fine. And when it will be for a given element, then it will be referred as Kij, and superscript there will be some number, okay, within parenthesis. So that will basically denote the element number. So these are all discussed in the lecture. Okay, I am just recapitulating that. So basically we need to understand the assembly process. Alright. So here the first question says that you need to calculate the global stiffness entry K13, okay, in terms of the elements contribution. Okay, as you can see here, this is what has been asked. But here if you look at this K13 means basically it's a entry in the global stiffness matrix. So this is node number 1, this is node number 3. But if you look at this closely, this the shape function n1, if I draw the shape function n1 in a different color, maybe in a green, so it is 1 here, okay, and it is 0 along the boundary of element 1, that is this boundary. Along this boundary it is 0. So this is what is n1, global n1, or you can say n1 in element 1. All right. Similarly, if I draw n3, let me take a different color, n3. So n3 is 1 here at node 3, and it is linearly varying to 0 along the same line. Alright, so this should vary linearly, even though it doesn't look like, but it should be linear. Okay, so this is n3. Alright, so n1 is 0 along this boundary, and it is 0 in all other elements. Okay, and is linearly varying in element 1. n3 is varying linearly in element 2 and is 0 in element 1. So k13, basically this a function n1 and n3, they does not have any common non-zero element. Okay, they are not non-zero, both of them are not non-zero in a given element. So that's why this value k13 will be 0. Alright, because n1 is 0 in element 2 and n3 is 0 in element 1. So that's why the k13 will turn out to be 0. If I go to the next k33, so this is the global entry that has been asked for. So k33, as you can see, k33 basically the shape function n3 is non-zero in 3 elements, in element 2, in element 3 and element 4, but it has different names. Okay, so n3 is basically shape function 3 in element 2, but shape function 1 in element 3 and shape function 2 in element 4. So it has different names. So k33 will be calculated based on these 3 elements. Okay, so basically k33 I can write, this will be same as k33 in element 2 plus it will be k11 in element 3 plus k22 in element 4. Alright, so these 3 terms will contribute to calculate k33. You can also do the same thing using connectivity matrix that I discussed in the lecture. So you can follow that and you can actually verify this. Alright, but looking at this, you can quickly do that. Okay, because shape function 3 is basically the local 3 in element 2, the local 1 in element 3, and local number is 2 in element 4. So that's how I can quickly answer this question. Similarly, k55 has been asked for, and k56. So let me go back and do that. K55. So this is 5. All right. So k55. This 5 is a global number because the local numbers are varying from 1 to 3 only. So as you can see, the shape function 5 is non-zero only in 2 elements, element 3 and element 4. Okay, so the local number corresponding to 5 is basically 2 in element 3. So that's why it will be k22 in element 3 plus you have k11 in element 4. Alright, so this is how this can be calculated. Okay, or you can look at the assembly, okay, or a connectivity matrix and do the same. But what about k56? The next question is about k56. So if you look at k56, so this is 5 and this is 6, and these are common in element 3. Okay, these are common in element 3. So they will be contributing only, or the contribution from element 3 will only be there. Alright, this is obvious. And 5, the local number is 2, the corresponding to 6, the local number is 3. So it is same as k23 calculated in element 3. Okay, everywhere else it will be 0 because k5 is non-zero in element 4, but n5 is non-zero in element 4, but n6 is 0 in element 4. Similarly, n6 is non-zero in element 2, but n5 is 0 in element 2. So those will not appear. Alright. So this is how you can quickly answer this. Then I will talk about one more, say force term F3. Let's take this case F3. So if I go back F3, again we need to understand the contribution of N3. Alright. So F3, okay, basically the local number corresponding to the global 3 is basically 3 in element 2, 1 in element 3 and 2 in element 4. So these are the components of each of these elements that will be contributing. So I will write this as F3 in element 2 plus F1 in element 3. Okay, element number will appear at the superscript, and F2 in element 4. So this is how you can calculate F3. Alright, because N3 will be 0 everywhere else except this element 2, 3 and 4. So that's why these three contribution will be there. Okay, so with this I will go to the next step, but as you can see, I have basically found the connectivity matrix, okay, and I have shown the assembled system also, okay. So if you have any query, you can raise here, I will address that. So as you can see here, looking at the connectivity matrix, you can form the global stiffness matrix and the global force vector, and you can address the same questions, okay. So I think these are understood because I have discussed it many times in the lecture. So this 1, 2, 3 at the top is basically the local numbers, and these are all global numbers. Alright. So if I have to see, say, sorry, if I have to see K66, okay. So this is the K66 here, and as you can see, 3 elements are contributing. You can look at here, okay. K6, there are 3 elements are contributing, 1, 2 and 3, okay. And how we can calculate, that is what has been shown here. So it will be contributed by K33 of element 1, as you can see from here, the local number is 3. Then 66 in element 2 will be 1, 1 in element 1, okay, sorry, in element 2, okay, and the last one is basically K33 of element 3. So that is how it is appearing. Alright. So these are all straightforward. Is there any question? Fine. So let's discuss about the next part. So as you can see here, I have shown the Lagrange element here and the serendipity element corresponding to p equal to 2. So these both are quadratic, but this is Lagrange element and this is serendipity element. So the first question goes like this: the step function n1 you need to calculate for Lagrange element. So I discussed many times. So this should be 1 and 0 at all other nodes. So if I draw it, it should be like this. It is quadratic. It should be 0 at all other nodes. Okay. So n1 is 0 along this, n1 is 0 along this, and it should also be 0 along eta equal to 0 and xi equal to 0. So xi equal to 0, it should be 0. Okay. So xi minus 0, at eta equal to 0, it should be 0, and then xi equal to 1, it should be 0, and then eta equal to 1, it should be 0. So that's how you need to form the polynomial. Now you need to calculate the coefficient. How to calculate the coefficient? So I said, say the coefficient is C1. Now we know that at -1 minus 1, n1 has to be 1. So if I put the value here, -1 minus 1, so it is -1, this one is -1, this is -2, and this brings -2. Okay, C1 times this should be 1. So this is 4, so C1 should be 1 by 4. Okay, that's how this answer is coming. Okay, 1/4 of xi into xi minus 1 into eta minus 1. Alright. So this one was the question. So similarly you can go for N5 also. Okay, but N5 you need to be little bit cautious. Let me change the color. So N5 is here. So N5 is 1 here. Okay, and it is varying quadratically. So it is 0 along this border and 0 along this border, and it is also 0 here and at eta equal to 0. Alright. So if I write this, so it should be 0 eta at eta equal to 0, it should be 0 in eta equal to 1, then xi equal to plus minus 1, it should be 0. Okay, so then you got the polynomial. Coefficients have to be calculated in order to make it 1 at 0.5. What is the coordinate of 0.5? The coordinate is 0, minus 1. Okay, xi equal to 0 and eta equal to minus 1. That brings minus 1, minus 2, and you have xi equal to 0, so that gives 1. This brings 1. So C2 times this is 1. So that will give you the coefficient. Alright. So as you can see, it has turned out to be minus half. Alright. Now let's go for N6 is similar. N9. N9, if I look at, N9 is actually the easiest one. N9 looks like this. N9 should be 0 in all the borders. Okay. So N9 is basically, you can say it is 0 at xi equal to plus minus 1 and eta equal to plus minus 1. So you can simply put as xi square minus 1 and eta square minus 1. Alright. And what should be the coefficient? Because the coordinate of 9 is 0, 0. So if you put 0, 0, then it becomes automatically 1. So the coefficient should be 1. Alright. Now let's go to a serendipity element. Okay, serendipity elements are non-trivial. So you have to be little bit cautious here. So first is N5, and then I calculated N2, and then N6 and N8. Alright, so let's go one by one. Say N5, if you look at N5, let me erase this part. So that I can make some space. Yes, so first I need to find out N5. For this, N5 is 1 and is 0 varying quadratically. 0 here, here and here. Only the thing is the internal node is missing. Alright. So if I look at the serendipity element, N5 looks like C5 is the coefficient and it is 0 along xi equal to plus minus 1 and eta equal to 1. So I will put it like this, eta minus 1 and xi square minus 1. This is not difficult. And then I will put the coordinate of 5 as 0, minus 1. So that brings C5, eta becomes minus 1, so it is 2. Zeta equal to xi is 0, so that brings minus 1. And this is equal to 1. Alright. So that gives me C5 equal to half. So that is how I calculated N5. But now if I need to calculate say N2, okay, or maybe N1, then before calculating N2 I need to calculate N6. And if I draw N6, N6 is basically 1 here, varying quadratically like this, and in 0 in these three borders. So that will basically help me to calculate N6 hat as well. That is not very difficult. So once I calculate N5 and N6, alright, then I will go for N2. Okay, that is what was the strategy. If you remember, I discussed in the lecture. So N2 is to be calculated for serendipity element as N2 linear. N2 linear, okay, that is already known to us. Okay, N2 is basically linear in xi and eta. Then since N2, if N2 linear is like this, N2 linear looks like this. Okay, it is 1 at node 2 and varying linearly along xi equal to -1 and eta equal to -1. Sorry, xi equal to 1 and eta equal to -1. And then at node 6, my N2 linear, so this is N2 linear, I am writing as N2 lin. Okay, so N2 lin is half at node 6, so I have to subtract half of N6, okay, that I already calculated, and similarly half of N5, okay. Alright, that will give me the N2 for the serendipity element. So you need to simplify it, but let me tell you what is N2 lin. What is N2 linear? N2 linear is basically 1/4 of, as you can remember, it is 0 in eta equal to 1 and xi equal to -1. So it should be xi plus 1, okay, and eta -1. Alright, so that is how you can write it, okay, but you need to check, because at 1 minus 1 it should be 1, so 1 it is 2, but this is -1, it should be -2, then it should be minus of 1/4, or you can say 1 plus xi 1 minus eta, like that you can write. Okay, so that is N2 linear, that is known to us. N6 we calculated here, N5 we have calculated, so you need to follow this, simplify it to get the N2 for the serendipity element. Alright, so I have addressed N8 also, similarly you can calculate. Okay, so I have addressed this. So let's come to question number 3. So if you have any query, you can post it here. So here what is given, a physical element is given, one physical element is given, the coordinates are mentioned here, okay, x and y of each of these nodes. It has been mapped to a master element, so in this case it is basically a right angle triangle, okay. So this is tau hat. If you remember, we discussed, we denoted the master element as tau hat, and we need to calculate basically the Jacobian matrix. Okay, we need to calculate the Jacobian matrix. So what we need to know, we if you remember, we said that x equal to x1 n1 hat plus x2 n2 hat plus x3 n3 hat. Okay, and what is n1? N1 is 1 minus xi minus eta. N2 hat is basically xi, and N3 hat is basically eta. So these things we substituted here. Similarly, we wrote y equal to yi ni, okay, at I goes from 1 to 3, okay, similarly, and we wrote these two expressions, okay. Then we know the Jacobian is basically del x del xi, del x del eta, del y del xi, del y del eta. Alright, so we'll take the derivatives, partial derivatives of each of these terms. So as you can see, if I calculate del x del xi from here, so del x del xi will be x2 minus x1, okay, so this should be x2 minus x1. Similarly, del x del eta will be x3 minus x1, so this should be x3 minus x1. Okay, so those are actually inserted in this matrix, and you need to calculate the determinant of the matrix, and you will see that it turns out to be negative. Alright. So the reason behind is this: in the physical element we have marked the number clockwise, in clockwise direction, whereas in the master element these are marked in anti-clockwise direction. Okay, so that's why this turn out to be negative. Alright, so basically we have to be very cautious while numbering the nodes. Okay, once we get the mesh from the software or maybe from your own code, you should ensure that your node numbering is done in the anti-clockwise direction. Okay, so that's why this problem has been given. Okay, you need to avoid this. Your determinant should be always positive. Okay, because if you remember, I said that it is the ratio of the two lengths in a 1D case. Then here it is basically the ratio of the two area. Okay, so that cannot be negative. Okay, let's see. You have any more? Fine. So if you do not have any query, let us discuss the last problem of the assignment. So in this case, we have asked you to basically implement a Gauss quadrature rule. Okay. Basically, if you look at MATLAB, it is already there inbuilt. Okay. But in order to develop the sense, okay, how it is done, so you can write a small code, okay, implementing Gauss quadrature rule, and that is the purpose of this assignment. Okay. So here we have asked you to calculate integral n1 n3 d psi d eta. Okay. So if you look at this n1 expression for n1 and n3, so when you will take the product of n1 and n3, you will get 1 minus I square and 1 minus eta square. Okay. So basically in the first problem we have asked you to integrate 1 minus I square, 1 minus eta square d psi d eta. So this is basically area integral. Okay. So this is an area integral. As you can see, we have put it in there here. So now the main idea here is basically, as you can see, your integrand is having quadratic terms. So if you simplify it, so you have 1 xi square eta square and xi square eta square. So you have quadratic terms, monomials, and in the product term you will be having biquadratic terms. Okay. So to do this, you just need to remember that in order to integrate pth order polynomial, so if your integrand is of pth order, okay, you have to take the number of integration points, or your number of integration points should be greater than p plus 1 by 2. Alright, p plus 1 by 2. Number of integration points should be greater than p plus 1 by 2. What is p? P is the degree of the polynomial, or you can say the degree of the integrand. So the maximum degree here is basically 2. So your number of quadrature points should be more than p plus 1, 2 plus 1 by 2. So that makes it 3 by 2, 1.5. So you cannot take a decimal this thing. So you have to take number of integration points as 2. You cannot take less than that. Then your integration will be incorrect. Okay, that is the purpose of this problem. So if you take a 1 point rule, when I say 1 point rule, basically it is 1 point in each direction. So you have to take 1 point in xi direction and 1 point in eta direction. So 1 point rule means your integration point is basically at the origin. Okay, xi equal to 0, eta equal to 0. So if you use that integration rule, okay, you will see your integrand value is 0.25. Alright. But whereas if you take two integration points, so when you use two integration points, in each direction you have xi is basically the location of those Gauss points are basically plus minus 1 by root 3 and the corresponding weight is basically 1. Alright. So there you will be having 4 integration because you have 2 integration points in each direction. So you have to evaluate this integrand at these 4 points while you will be using 2-point rule. You have to evaluate your integrand at these 4 points, multiply with the corresponding weight, and then you have to sum it up. Okay. So that you have to do, either you can do it by hand or you can write a small code to do that. Alright. So, but when you are using a single point rule, you will be evaluating the integrand only at the origin 0, 0 and you will be multiplying by 2. Alright. So here your integration value turns out to be, when you are using 2 Gauss point rule, your integration value becomes 0.22. Now if you use more integration points, you see there is no change because you have already reached the accurate result. Okay, even if you use more number of Gauss points, that will unnecessarily basically be time consuming. Okay, you have to spend more time to integrate. Okay, calculate the integration that you don't need to do because with 2 points you have already got the accurate result. Okay, so to realize this problem has been formulated. Okay. So I'll wait for a few minutes, and then in case you have any query, you can put it in the chat box. I'll try to address. How many participants are there? Oh, these 3. So including us, excluding us. Yeah, so I have received. I do not know whether it is a question or a suggestion. State the application of FEM in the industry. So basically, because this question has been, or query has been posed late, so I will try to address it here as much as possible. So all of you have seen the automobiles. So these complicated structures, you cannot have a analytical solution under certain conditions. So be it stationary, dynamic, or maybe under say while it is crashing. So all under these conditions, if I have to understand the behavior of this structure, okay, or maybe if I have to make it more efficient, okay, then in that case we cannot go on making prototypes and testing it, okay, because that is very costly affair. So in that case, we can build simple models, okay, of the designed chassis, and then we can do the testing under stationary case or dynamic case, even under crashing conditions, okay, and that helps us basically to understand what modification in the design that is required in order to make it more efficient or make it more economic or make it more stronger, okay, while undergoing some accidents or maybe while undergoing some impact, okay. So those this is one example. Apart from that, any other problems, any other physical problem, okay, if you look at the governing, if you know the governing differential equation, basically you can make use of the finite element as a numerical tool and simulate the domain, okay, simulate the behavior of the domain under certain boundary conditions and initial conditions. Alright, so this comes very handy particularly for engineers, okay. You don't have to always build a prototype and test it before coming to a conclusion that the design is good or bad. You can always simplify the system, okay. You can assume certain conditions which will basically simplify your problem, and then you can simulate it using finite element method, okay, to see whether your design needs any modification or uh, you can basically design it in a better way. All right, and finally once you are happy with the simulation behavior, then you can build a small prototype and you can test that under real situation, okay. So that in that way it comes very handy in industry, okay, be it automobile industry or any other design related industry, it comes very handy. All right, so in the ultimate objective of this course was to give a basic idea about the different methods, okay, using which you can actually uh, derive the algebraic equation, okay, discrete algebraic equation of a given boundary value problem, because the boundary value problem most of the cases it is in the form of a partial differential equation along with certain boundary conditions and initial conditions. So what are the steps needed in order to derive a set of algebraic equation which we can solve very easily, okay, because that will give us an approximate solutions, but even then that is very easy to derive, and then from there we can actually have a very good understanding about the response of the system, okay. So this is basically a numerical tool that can be used in any engineering fields that are being used, okay. It is not like this is used only in mechanical design. This can be used in any other field related to design, or maybe in any physical system you can design based on this tool. All right. So I do not have any application right now because when I started this there was no query, but I think hopefully I have addressed your issue. All right. Thank you. Done. Some time left. Okay, fine, no problem, no issue. Is there any lag in this one? Hmm? Yes. So if you have any more question, you can post it. We will wait for 1 minute or so, and then otherwise we will close it. Fine. Since there is no more question, then we will close the session for today. Thank you.